Okay, so now we move on to the topic of experimental design. So the learning objective for this chapter is to understand how best to design an experiment. So that's perhaps a rather optimistic learning objective, but at least to have some understanding of how to design an experiment. So we're often concerned with the analysis of data that's been generated from an experiment, but it's wise to take the time and effort to organize the experiment properly to ensure that the right type of data and enough of it is available to answer the questions of interest as clearly and efficiently as possible. So this process is called experimental design. So that means that the specific questions that the experiment is intended to answer must be clearly identified before carrying out the experiment. We should also attempt to identify known or expected sources of variability in the experimental units, since one of the main aims of a designed experiment is to reduce the effect of these sources of variability on the answers to questions of interest. That is, we design the experiment in order to improve the precision of our answers. But it's important to understand that optimizing the experiment in some ways may make it less useful in others. So for example, minimizing the prediction error may not allow us to fit polynomial or other nonlinear models. So we do need to be careful. So let's first talk a little bit more about the language. Some of this we've introduced before in the analysis of variance, but just to make sure we're on the same page. So the main effect, this is the simple effect of a factor on a dependent variable, is the effect of the factor alone averaged across the level of other factors. Whereas the interaction is the variation among the differences between means for different levels of one factor over different levels of the other factor. So for example, if we had a cholesterol reduction clinic that had 2 diets and 1 exercise regime, it was found that exercise alone was effective and diet alone was effective in reducing cholesterol levels. So in other words, there is a main effect for exercise and there is a main effect for diet. But it was also found that for those patients who didn't exercise, the 2 diets worked equally well. The main effect, so that's the main effect of diet. Those who followed diet A and exercise got the benefits of both. So that's the main effect of diet A and the main effect of exercise. However, it was also found that those patients who followed diet B and exercised got the benefits of both plus a bonus. So that's an interaction effect. So that means that they got the main effect of diet B, the main effect of exercise, plus they got a positive interaction effect. Okay, blocking. So what is blocking? So this is the procedure by which experimental units are grouped into homogeneous, that means similar, clusters in an attempt to improve the comparison of treatments by randomly allocating the treatments within each cluster or block. So that's trying to make sure that not just due to the random allocation, but in our design process, the different treatments get individuals who are as similar as possible. So randomization is the process by which experimental units are allocated to treatments. So remember, the experimental units are the basic objects upon which we're carrying out the experiment. So that is a random process. It shouldn't be subjective or biased approach. The treatment should be allocated in such a way that each treatment is equally likely to be applied to each unit. So randomization is generally preferred because the alternatives may lead to biased results. The logic is similar to why we need random samples in order to have samples that are representative of our population. So the key point is that randomization tends to produce groups for study that are comparable not only in the known factors, which should be a part of our design, but also in the unknown factors. So this is critical because in most situations there are unknown factors, certainly if we're dealing with social or biological experiments. So it might be the case in some physical experiments that there really is no other unknown factors because we think we can control everything, but most experiments that isn't the case. There are some possible unknown factors which could have influenced our results. So the standard analysis of variance F test that we talked about earlier assumed that the treatments were fixed but had been allocated randomly to subjects. So, blinding. So particularly in a medical experiment, the comparison of treatments may be distorted if the patient, the person administering the treatment, or those evaluating it know which treatment is being allocated. So it's therefore necessary to ensure that the patient and or the person administering it and the trial evaluators are blind to which treatment is allocated to whom. Blind to means they don't know. So this is not just medical, but actually any situation where we're doing a randomized trial. So sometimes the experimental setup of a clinical trial is referred to as double-blind. That is, neither the patient nor those treating and evaluating their condition are aware. Now, of course, that's not always possible, right? Sometimes, for example, if you're doing surgery, if you're going to remove somebody's limb, clearly there cannot be a double-blind situation, right? But it might still be important, though, to at least have a single blind in which the patient only is unaware of the treatment received, or in other situations, it may at least be possible to have a blinded evaluation. But a double-blind study is the most scientifically acceptable option because it reduces the risk of bias. Now, placebo. We talked about placebo in the analysis of variance chapter. A placebo is an inactive treatment or procedure. It literally means I do nothing. So the placebo effect, which can be a positive or beneficial response, is attributable to the patient's expectation that the treatment will have effect. So this is sometimes linked with the Hawthorne effect, which is slightly different. The Hawthorne effect is the effect due to attention being paid to people. In other words, people respond positively to being assessed or measured. So clearly the Hawthorne effect should occur for all study participants as long as the level of interaction is similar. So this means you have to be careful. So for example, if it wasn't a medical treatment, but it was some form of intervention where people were having somebody giving them feedback, or there was some connection, you want the level of interaction to be similar. Otherwise, the participants who get more attention paid to them may have a more positive result just because of the Hawthorne effect, rather than the intervention itself is having differing effects. Now, we need to be aware of ethical concerns because clearly it may be unethical to randomize the treatment allocation of treatments to humans. Why? Well, if, for example, we know already that one treatment is much better than another, or we already know that one treatment is much better than the placebo, then clearly there would be an ethical problem to give somebody a treatment that we know is inferior. So sometimes we have to use the current best treatment for comparison instead. This can be complex when there are risks, in other words, side effects, for example, as well as benefits of treatment. When it is unethical to not provide the one treatment being considered, one possibility is a weight control study where we compare before, during, and after treatment to see if the effect persists for each individual. It may also be important to look at cost effectiveness, which requires collecting data about the full cost of treatment. And of course, this is in addition to the risk and the side effects. So note that all studies that involve treatment of or personal data collection from human or animal subjects require ethical approval. For clinical human studies, this involves the IRB. This is the Institutional Review Board of Hong Kong U, which is linked with the Hospital Authority. For live animals, it involves the Committee for the Use of Live Animals in Teaching and Research, while for other studies with personal data or human subjects, it's the Human Research Ethics Committee for Non-Clinical Faculties. Okay, so let's start to look at a few designs. So a completely randomized design means that all the factor combinations are allocated to the subjects completely at random. Okay, a randomized complete block design is where we match the subjects according to a variable that we wish to control first. The subjects are put into groups or blocks of the same size as the number of treatments, and then the members of each block are then randomly assigned to our different treatment groups. So let's look at an example. You have a researcher who is carrying out a study of the effectiveness of 4 different skin creams for the treatment of a certain skin disease. He has 80 subjects and plans to divide them into 4 treatment groups of 20 subjects each. So using a randomized block design, the subjects would be assessed and put into blocks of 4 according to how severe their skin condition is. So the 4 most severe conditions would be the first block, the next 4 most severe would be the second block, and so on all the way up to the 20th block. And then within the block, those 4 members are then randomly assigned 1 to each of the 4 treatment groups. So this ensures that the 20 subjects in each treatment group cover the range equally from the 1 chosen from the 4 most severe all the way through to 1 chosen from the 4 least severe. So in that sense, we've made as closely as possible ensure that it's a fair comparison between the treatments as regards severity of the skin condition, and we would be relying on the randomization for the impact of anything else that might influence their response to the different skin creams. Okay, so a factorial design. What's a factorial design? That's where we want to evaluate 2 or more factors simultaneously. Until only about a century ago, people used to believe that we could only study 1 factor at a time. So factorial designs, which were originally developed in the agricultural field, were used to evaluate 2 or more factors simultaneously. So the treatments are combinations of levels of the factors. The advantages of factorial designs over 1 factor at a time is that they're much more efficient and they allow interactions to be detected. If you only study 1 factor at a time, you will never be able to identify any interactions. So a full factorial design means you've covered all combinations of the factor levels an equal number of times. So if they are covered more than once, this means we have replicates, which we mentioned before. So a full factorial design, of course, you can understand then, that means a large number of combinations if the number of factor levels and the number of factors is large. So that may be not feasible, right? We may simply not be able to have enough subjects to cover all the combinations. So one possibility that we can consider is something called a fractional factorial design. So a fractional factorial design means a design that only covers a simple fraction of a factorial design and is a full factorial design for some subset of the factors. So for example, it could be a full factorial for all pairs of the factors, but is not covering all the combinations. So that will have some limitations. It means we won't be able to estimate all the interactions. The more complex interactions we won't be able to include. So that means implicitly we are assuming that the more complex interactions are not important. So before we move forward, let's talk a little bit about what the key principles are. So the idea is that when our data collection can be fully or at least partially controlled, we can design an experiment in an optimal way. But we're going to look at 4 different types of question. The first one is that our key question is which factors affect the response and how. So this is, if you like, the pure scientific approach. We want to have a full understanding of both which factors affect the response and how they affect it. That's the pure scientific approach, but we often may have resource constraints or some other constraints. That means we can't answer that most general question. So the second type of question is, what is the optimal combination of factors to maximize or minimize the response? So for example, this could both be a treatment where you want to minimize some bad effect, or it could be some intervention where you want to maximize the yield or maximize the outcomes, right? So that could be, say, an educational situation where you want to identify what combination of teaching elements gives you the best response in terms of the student's understanding. The third type of question is we're trying to essentially do a screening approach. We want to know which factors look like they have the greatest influence on the response. So we might have a very large number of factors, but we need to narrow things down. We need to find out which are the ones that we need to look at more carefully. And then lastly, in a situation where we maybe only have a relatively small number of factors, but we want to understand the type of relationship they have. So is it linear or quadratic and the like? So how would we respond to these different types of question? So for type A, which means which factors affect the response and how, we usually want a full factorial design, which means generating all possible combinations of the levels of the factors, which, as I said, can be a large number as the number of factors and or levels increase. So for B, where we're trying to do the optimal combination to maximize or minimize, we usually assume a quadratic response, and then we want to choose the data points to help us find that either maximum or minimum point. So this is called a response surface design, because you're assuming that this is a quadratic surface and you're trying to find the minimum or maximum. So if you think of it as being like an umbrella, you're saying you're sampling points on the umbrella and you want to know where is the minimum of the umbrella if the umbrella is with the handle upwards, or you want to find a maximum point of that umbrella surface if the handle of the umbrella is pointing down. So for the third type, the greatest influence, this is what we call a screening design. So we usually assume only 2 levels for each factor, and we again use a fractional factorial design. So we're usually assuming that all the interactions are small, or that at least all the higher order interactions are small, and we focus on the main effects of each factor. So for example, if we had 10 factors with 2 levels each, that's 2 to the power of 10, that's 1,024 possibilities. A 1/8 fraction would be 128, a 16th fraction would be 64, a 32nd would be 32, a 64th would be 16. So a 64th with 16, that's still enough to estimate 10 main effects, but we wouldn't be able to estimate any interactions, right? Okay, so that's if we have 2 levels. Sometimes we might assume 3 levels, sometimes we need to do that, but you can see the number of possibilities gets large very quickly. So only 5 factors, but with 3 levels each, it turns out that's 3 to the power of 5, which is 243 possibilities. So 1/3 fraction would be 81 and a 1/9 would be 27. Okay, so these are the sorts of designs we could do. What about D? So for D, we need data spread out over different levels for the factors in order to identify any nonlinearity. So this is only feasible for a small number of factors, and we need a minimum of 3 levels in order to have any chance of identifying nonlinearity at all. Right? If there's only 2 levels, we cannot by definition identify any nonlinearity. So there are some general principles which we always will try to follow. First of all, we try to keep the design balanced, meaning an equal number of data points for each factor level. Secondly, we try to take values as extremes. You remember when we were looking at regression models, we said that we want the range of X to be large in order to get good estimates. That also means that the third one, we want values at combinations of extremes. Fourthly, we do usually want some points near the center to check for curvature, so particularly for a question type D. And then lastly, this is very important, we randomize the assignments of the data points to minimize any uncontrolled for effects and interactions. So let's start with a very nice simple example of a fractional factorial experiment to see which of 7 binary factors affect the speed when riding a bike. So this is not a very serious example. So our 7 factors are whether we use a low or high gear, whether we use a dynamo or not. So I don't know whether you know what a dynamo is. A dynamo is a little thing which you connect to the tire to generate electricity to make the lights work. So in the days when batteries were expensive, instead of relying on a battery, the dynamo meant once the bike is turning, the wheels are turning, you're generating a little bit of electricity, which was enough to make the lights work. What is the position of the seat? Is it up or down? The tires, are the tires being pumped hard or soft? Are the handlebars adjusted up or down? Did you have breakfast or not? And are you wearing a raincoat or not? Okay, so we only have 8 observations, which is 2 to the power of 3. Clearly we would need 2 to the power of 7, which is 128 observations for a full factorial experiment. That means that even for main effects, we cannot estimate the residual. We can only order the effects, not test their significance. So we get a result something like this. So we get a perfect fit because we only have just enough data points, but at least we can order this. So the p-values are not to be taken seriously. The t-ratios are here telling us the relative importance. So we can see that gear is one key thing and dynamo is a key thing. Everything else is relatively small. Okay, so in that situation, we might repeat this with just looking at the gear and the dynamo. So next we're going to look at a rather more serious example. This is a full factorial experiment with 5 binary factors, but no replicates, where we're trying to identify what affects the output of this reactor. So we're going to try fitting the main effects and the two-way interactions. So let's have a look at what results we get here. So here we've got reasonably good fit. The adjusted R-squared is about 95%, meaning we're able to explain most of the variability using these main effects and two-way interactions. But this is quite a complex model in that you can see that of our 31 degrees of freedom, we're using 13 in the model. Again, if we look at the sorted parameter estimates, you can see that the catalyst is very important. The combination of temperature and catalyst is important. Concentration and temperature is important. Temperature is important and concentration is important. And it looks like the rest aren't. So in other words, it looks like feed rate and stir rate do not influence the outcome, right? We just need to look at the combinations of catalyst, temperature, and concentration. And of those, the only one that isn't significant is the concentration by catalyst interaction. Okay, so that would enable us to already have a pretty good idea of what the key factors are. We could repeat the fit with just those 3 main effects and the two-way interactions to look a little bit more carefully. That's a much simpler model that hopefully will help us identify what's going on. Okay, so that brings us to the end of what I'm going to talk about with experimental design.